and the last talk will actually done by myself and a bit on still in the QA setting, but with a different spin because we are now tackling not a single objective problem, but a multi-objective problem. And I would like to start with a little bit of introduction. I mean, we've seen a lot of stuff during this course of the workshop. We saw, for example, also the TSP problem in multiple occasions. But maybe I will start with a bit of experience I had when I tackled optimization problems with quantum computing. And then, for example, the TSP problem, you all know it. For example, if you look at this small example, I mean small, so you take all state capital cities of the US, without Alaska and Hawaii because it's difficult to travel there by road. So you have 48 factorial possibilities. But when I did this way back during my PhD, so this is old data, some to say, but I solved it then with Gurobi on my laptop here. And this was done around 5-6-ish minutes. And Gurobi said, okay, this is the optimal solution. I can prove it. The same is, for example, if you look at more, and we've seen this by Oliver, the unit commitment problem. Not by Oliver, by David. We've seen this by David, the unit commitment problem, where you want to find like an optimal schedule for your power plant and energy production. This is a bit more practical than the TSP problem, but still, if you look at this, then you see, and for example, these are now the solutions by Gurobi, and you see that, for example, for 2,500 units, you have an optimizer time that is below 250 seconds. So also, you can solve this quite fast, and this means, of course, just because an optimization problem, and this is my take on it, is NP-hard, like complexity-wise, and both of these problems are famous NP-hard problems, it's not necessarily hard to solve this in practice with your state-of-the-art commercial solver or your state-of-the-art special purpose algorithm. So to even achieve quantum utility or quantum advantage with D-Wave, with QUBOs, with IBM, this is like really, the bar is really set high. So I mean, some like D-Wave, they postulate, okay, we have quantum advantage, but especially in optimization, we have 70 years, 80 years of people that are working on software, on quantum algorithms. So this to catch up in only 10 years, I think that would be a major milestone, and I think it won't be possible. But just because now that was the bad news, but still, I don't see that quantum optimization is dead. So I think we can all resume our research here, because first of all, still there is the potential for quantum algorithms to succeed. I mean, we need maybe better algorithms, we need algorithms for fault-tolerant quantum computers, we need fault-tolerant quantum computers, and also, I mean, we still do something good, I always tell myself, because when we excel with new algorithms, this puts the pressure on the classical people, and I mean, some of you also work on the classical side, so to say, okay, you got pushed by the quantum people, and now the classical people have to respond. I mean, it's the same when D-Wave published the quantum advantage paper, one day later, the tensor network people from the classical side said, we still are better. So this, I mean, and this is some nice competition that will thrive ultimately to better algorithms, be it classically or quantum. But still, from my perspective and my experience, there are classical problems that are really, really hard to solve, both from complexity, but also from really wall clock running time. And this is, for example, you have a difficult objective function, like you have nonlinear, non-polynomial. I mean, you have gradient descent, you have some genetic algorithms, but then you resolve to heuristics. Or you have implicit functions. You cannot really write this down as a mathematical formula. Or you have, for example, multi-objective problems. Then you have uncertainty or missing data. That is what we've seen with Oliver. You have robustness, you have stochasticity, where you, for example, see, okay, for the cargo ship, I don't know where the demand will be in the next day. So you have certain uncertainty, or you don't, the data is only revealed over time, so you have like an online problem. Then you have other problems, for example, in logistics, where you have multi-stage problems, you have scheduling problems, where you have some mixture of those, and these are really hard. So there are special purpose solvers or algorithms for these, but they are way off the pace, for example, for TSP or stuff that Gurobi is designed at. And so my idea is, if you want to have quantum advantage or quantum utility really fast, you have to look where the heuristics excel. And these are some of these problems here. And I want to focus on one of this, and this is multi-objective optimization. And we recently published a paper on arXiv, and it's currently under review. And I did this together with my colleagues Ivica, Tom, Yannick, Michael, and Zakaria. And this is a QAA-based solver for multi-objective optimization. And since many of you are not familiar with multi-objective optimization, so what is it? Well, multi-objective optimization problems tackle real-world problems that have multiple but often conflicted objectives that need to be optimized simultaneously. So, for example, you buy a car, you want to have a cheap car but also a fast car, and of course, these two objectives are conflicting, because a fast car would be something like a Tata Nano, not really a Tata Nano, this would be the slow cars, but the cheapest car, but the fast car would be something like Koenigsegg. And this is not cheap. This is, really, really expensive. So, and this is also not relevant for when you buy a car, but also it's relevant in many practical things that we also work here at ITWM, for example, portfolio optimization, where you want to find an optimal investment, where you want to maximize your return and minimize your risk. So this is bi-objective by design, especially for the well-known Markowitz model. Then also what we are doing here at ITWM is cancer treatment, where you want to find not an optimal investment, maximizing return and minimizing risk, which stands on the slide, but you want to, of course, treat the cancerous cells as much as possible while you don't want to harm the healthy tissue as much as possible. So there you also have two objectives that obviously conflict. And so this is the practical part, but how do we do this mathematically? So a multi-objective optimization problem looks like follows. I mean, you have your feasible set X, you want to minimize a function, but the function is not scalar valued, but it's vector valued, consisting of functions f1 to fk. And so this looks, if I have just two functions of those, this looks like this. And clearly here, there is no one distinct optimal solution here, but we need another concept of optimality, the so-called Pareto optimality. And we say that some of these images are non-dominated, which is our stance on optimality, if there's no other image that is better in every objective function and strictly better in one. And so, for example, if we look at this, then we see, we see for this solution here, this solution below here is better in the first and also in the second objective function. So this one is not Pareto optimal because it's dominated by this one below. But on the other side, if we look at this one, then when we see, for this one, there are solutions like these one that are better for the first objective function value, but they are worse than for the second objective function value. So there's nothing here in this green area, and thus this is a solution that is Pareto optimal or non-dominated, and the corresponding solution is called efficient. And the set of all of these non-dominated solutions here that are now marked in gray are the Pareto optimal or Pareto front or the Pareto optimal set. And for a full introduction, you can look at the following work by Matthias Ergot, the book Multi-Criteria Optimization. It's not for free, but I've heard that there is an Iranian page somewhere that provides you with the PDF. If you don't want to go to this gray zone of legal activities, you can also take a look at my thesis. There's the QR code. There I also provide you a quick introduction into multi-objective optimization. Yes. So in summary here, so multi-objective problems are highly relevant in practice. Also, they are NP hard, and usually the set of Pareto optimal solutions is intractable, so exponential in the encoding size of your input. So this makes it extra hard, so to speak. And so this makes it the ideal playground for quantum algorithms. And I'm not the first one, so there exist already some algorithms regarding this. For example, there's one by Baran and Viagra, which have an approach with quantum annealer, but they use a weighted sum to transform these multiple objectives to one objective. So they have some aggregation function, and so they can only find so-called supported non-dominated images, which are only a subset of the non-dominated images. So this is like the first approach, but it's not like providing like the full set of the Pareto front. And then the same authors also did a multi-objective version of the Grover adaptive search, and this flags the solution if it's not dominated. And the algorithm returns then only one non-dominated image for a given starting point. So you have to reload this multiple times with random starting points, but still then you cannot ensure you find like the whole Pareto front. The first true multi-objective quantum algorithm has been done by Ekström, Wang, and Schmidt, and they provide a multi-objective variant of QAA that we will we'll see in a short. And most recently there was another algorithm by Cotil et al. That is similar to the first approach, but instead of quantum annealing, they use a QAA, and they have a pre-trained QAA sampler that provides them good solutions for this weighted sum approach. And they use this because you don't just get the optimal solution, but some solutions that are falling behind, and they could really well approximate the Pareto front. Yes, and I would like to go to the work from Ekström and Wang and Schmidt, and we expanded this indeed. So what they do, and also what we do in parallel, but they were faster in publishing their paper, is the following. So this is your basic QAA approach. You have your problem unitary, your mixer unitary object for your objective function, and you do this like for each of the you repeat this like p times. But now what they are doing, and also what we are doing, is the following. You don't do that just for one objective, but you now have several objectives, so you just repeat this. So you have mixer and problem unitary for your k objective functions. This is one block, and then you repeat this p times. And you measure this, you have your beta and gammas, you have a whole lot more of beta of gammas because you have this for each objective function, and you optimize this with a classical solver, and you do your iterations just you do as your normal QAA. But one question is, okay, the measurement here is done, you get the solutions, you evaluate the solution by your multiple objectives, but the classical solver needs a scalar input because it needs to extend the value, how good is this circuit. And for this, there's one existing measurement or metric that's stemming also from heuristics, which is the so-called hypervolume. And for example, given a reference point over here, and you have your non-dominated images around here, you calculate the hypervolume of this blue area, and of course this blue area increases once you get closer to the actual real Pareto front. So this is a measure. So if this is increased, then also you have a closer approximation, and you take this one for the classical solver as the objective function. But this is indeed a bit of a drawback because, I mean, usually you have a multi-objective, you stop here with a multi-objective, and then you transform it to a scalar one, but basically we don't want to do that because we want to solve the multi-objective problem. So, and also this calculating the hypervolume is a bit expensive because it's a graphical thing. Also, if you not just have 2 objectives, but you have like 10 objectives, this is really computational demanding. So we thought of, okay, how can we improve that? And we did also some other improvements regarding the mixers, regarding the warm starting. We test a lot of stuff, and I want to just highlight the one part that is for me like the most important thing here. And this is the idea, okay, we propose another classical solver because there are classical solvers for multi-objective optimization. And we use this one as a classical heuristic to optimize our betas and gammas. And what we do is a so-called quantum NSGA2. NSGA2 is a famous multi-objective heuristic. It stands for non-dominated sorting genetic algorithm number 2. So you know there's a 1, but there's also a 3 currently. And this goes as follows, and I will just introduce this while I also will introduce how we do this with the quantum version for this. And we start with a random population of solutions classically, but for the quantum part, we start with a random population of these parameters of the betas and gammas. Then we evaluate, classically, we evaluate the objective function for each of the solutions in this population. For the quantum version, we run our circuit for every parameter set, and we're using a distinct number of shots. We measure this, and for every sample of the sample set, we evaluate the objective function. And now there is a major change. So for the classical one, you see, okay, we calculate for all our solutions, we have now the objective function value, we calculate the Pareto front, and we see, okay, this one here would be the Pareto front, the dark blue one, but we don't stop there because it's a non-dominated sorting. So we say, okay, once we have found the first Pareto front, we also take a look at the next one. So given that these are, the dark blue ones are off, so which would be then non-dominated, which is the light blue one, and then we repeat this until we have a sort of sorting by layers of all our solutions. And then we would say, okay, we calculate a crowding distance that says, okay, we get rid of some of, for example, half of our population that uses, for example, okay, we only take the one, for example, we take only the ones that are currently non-dominated, plus some of, for example, the second batch. For example, if we only have like a population of 10, but for example, we have, or let's say we have only a population of 5, then we would do the first 4 of our original Pareto front, plus 1 of the blue one. But to check which one of the blue one taking, we need this crowding distance as some trade-off. And then we apply genetic, because it's a genetic algorithm, we apply also some genetic ideas like selection. So which one do we select for recombination? We do some crossover, so where we recombine solutions, and then we also do some mutations. For example, in a binary setting, we do a bit flip or so. And then we repeat this process, and this is well working classically. So for the quantum version now, we do it a little bit differently. Now we have our, for example, 3 parameters that we are using. And we now check, we do the same for the solutions we have obtained. So we sort them by their non-dominance. But then we are having, but what we are then having is that, okay, these solutions are assigned to certain parameter sets. And then we take, we assign, okay, if for example, P1, the parameter 1, has solution in the first Pareto front, so this is assigned to the first Pareto front. The same is true for P2, which has 2 solutions over here, but for example, P3 has only a solution in the second front, so this gets assigned to the second front. And with this, we have an ordering regarding Pareto fronts also for the parameter sets, not just for the solutions. And then what we also do, the crowding distance of the parameter set, we also need this as a trade-off to decide where we do this, the split for the population, is then also similarly assigned by the crowding distance of its samples as we would do for the classical part. And then we also apply the selection, crossover, and mutation, and we repeat this process. And we tested this, and our setting we used the so-called unconstrained multi-objective combinatorial optimization problem, UMOCO. We tested this with up to 20 variables on the Qiskit MPS simulator, and we compared this with the existing implementation of NSGA2. And what we saw is, okay, well, first of all, this one here is the NSGA2 classically, so we see this still outperforms our quantum version, both the one by Ekström, Wang, and Schmidt, but also our ones. But we saw, okay, this one here, the light gray area, so this, we have some overhead, of course, because we use this multiple times with the parameters, but then we see that our solution, and measured by the hypervolume, so the actual area we are covered, excels here. So we have some improvement over time where we are better. And we did a little bit of looking into the glass bowl to check, okay, if, like, for example, given the roadmap of IBM, and we can, like they for example, the gate execution time will increase as they promised us, then this line will dramatically go closer to the green line. But I mean, this is, given that the hardware will excel. So for now, we just say, okay, it will be, and also, I mean, this is on a simulator, so we need error corrected and also fault tolerant qubits here. Okay, and this is all except for one small outlook. We are also, and this is what current work is, we try to extend the results of Cotil et al. With the QAA-based sampler, and the idea here is now that we try to use the QAA both as a warm start, for example, for an exact multi-objective algorithm, but also, for example, for the NSGA2. But also we try to use the exact algorithm and NSGA2 as the somewhat steering part that gives the QAA-based sampler the correct weighted sum parameter lambda to steer it in the proper direction where it should sample. And this is what we are currently doing now, and we hope that we have some really great results soonish. Yeah, and with that, I'm at the end of my talk. Thank you very much. These are my references just for completion. Yeah. And I already see a question. Yeah. No, you don't need that. So you can assume that if the I mean, of course, for the percentage shown in the last graphic, I knew the proper, so to see, okay, but you can assume that it's more like a heuristic. So if the hypervolume increases, you will get closer to the actual Pareto front. Yes. So the only thing you need is your current set of solutions plus a reference point you have fixed in it for the start, and you could do like the overall worst solution you could think of. So you want to do the real complete Pareto front. So usually you want to recover. Yes. From a theoretic point of view. I mean, in practice, you only need one solution, but it's, from our experience, always good to provide the decision maker, not just with, this is the one solution based on your preferences, but sometimes, as you know, the data is uncertain and also the preferences of people are uncertain. So it's always good to give them like some alternatives, and for that you need some analysis of the Pareto front. And I see a question over there. You go back to your NSGA. This one or? Yes, this one, exactly. It helps you rank your Pareto sets, as in the Pareto set 1 is here the best one because everything is in Pareto. And all of its solutions are in Pareto. 2 is technically because some of it are in none of it are in the Pareto. Yeah, you grab for each of the parameter sets, you have executed your circuit, you get a set of solutions, and you get from all those parameter sets, you grab all the solutions together, you rank them, and you know, of course, which solution corresponds to which parameter set, and then I get, from the ranking of the solutions, I get the ranking of the parameter sets. Okay, then there's one question in the back. Usually, the mixture yeah. Yes. Well, we use it as a ground state for each of the objective. So for the objective functions. No, for the ground state. For the ground state, but we do this individually for each objective function, like you would do for the. So it's not the same for each So the mixer is different for each objective function. This is, yeah. I mean, there were some lengthy discussion with one of IBM whether this is the proper way of doing it. We did also try some other mixers, and yeah, the IBM people, and this is the paper by Cotil, is, for example, very crystal clear that you shouldn't do like the a mixer and also a problem Hamiltonian for each objective function, because you get like a really large space, but it still works. So okay, maybe one last question, but then we. Is it possible to design a pair problem this year, the sort of mix with the towards non-dominant states? We have thought about that to maybe like incorporate like non-dominance into the mixer, for example, because we know that there's like a Grover oracle for this, but we haven't succeeded yet because this was really long circuit to do that. Maybe based on the other papers we have seen here, maybe there is a better solution to this, but it's definitely worth investigating for future research.